coming all the way from New Zealand, is getting on a plane tomorrow, so we need to take him to Hoboken tonight. Please welcome Thomas.
See if this will wake up. Nope, it's thinking. Yes, good. Okay, so thanks to Jared for inviting me. I met him at the Bioconductor conference in June, last time I was in New York, and thanks you all for coming. And so I'm going to talk about the survey package, basically. All the materials are on GitHub. So first, why should you care about the survey package? Well, one of the big reasons to care about multi-stage survey analysis is free data. The government and various other large organizations spend an enormous amount of money collecting data and then just sticking it up on the web for you to use. So on health, there's the National Health and Nutrition Examination Surveys. There's the National Health Interview Survey. There are more localized ones like the California Health Interview Survey. I'm sure there are New York ones as well. There's the Current Population Survey, which is where the unemployment rate comes from. There's surveys on attitudes and how they change over time, like the General Social Survey and the National Longitudinal Study of Youth. And then there's the American Community Survey, which has got questions on just about everything, except, as I found out today, religion, which isn't in there for some reason. So there's a lot of free data. So the other thing is you might be designing your own data collection and want to do something a bit more sophisticated than just picking people at random. However, when you go and look up what to do with these surveys, when you go to the documentation for these surveys, it comes with scary warnings about how you don't try this at home and so on. They say standard statistical software packages don't take into account all this really important stuff, and they tend to get the wrong, they generally underestimate the variance of a point estimate, sometimes substantially so, and you don't want that. So, and then if you try and look at textbooks on survey analysis, they have a strong tendency to look like this. And you can sort of get the impression that survey analysis is primarily about the care and feeding of subscripts. So, there are a small number of things that you actually do need to know about surveys in order to analyze them. But most of the rest of the stuff, only the computer needs to know. So there are textbooks full of formulas. Those formulas are not interesting. So some formulas are interesting. They explain how things are done. If you understand them, it's really helpful. The formulas in survey textbooks are computational special cases of a very simple general formula. They're in there because the very general formula takes time quadratic in the sample size, and so you need to have computational special formulas. But you don't need to think about them. Somebody's worked them out, they've been implemented, and they're not interesting. You don't learn anything from understanding them. There are some things you do need to know. And so R is one of the good ways of doing survey analysis. Stata is another. Stata has very good survey support. SAS, somewhat unusually, has never been the industry standard, and that's because there was another sort of Fortran era program called Sudan that was the industry standard, and that's been fading away a bit recently. So at least we don't have SAS as the competition. The competition is really Stata. So there's three things you need to know about: weights, clusters, and strata. Weights, it's one of these words that's overloaded in statistics. There are several different meanings of weights in statistics. What it means in surveys a weight of 100 means this person represents 100 people in the population. Perhaps, the sort of canonical view of this textbook view is that means you sampled this person with a probability 1 in 100. But there's a whole lot of other complicated things that often go into the weights. Non-response adjustments for people who don't reply, frame corrections for when you've got this list of buildings, but the list of buildings is 4 years old and some of them have been knocked down and new ones have been built. Household size correction, telephones per household, all sorts of stuff. But the weights generally get given to you. And so sometimes we oversample subgroups of people, and so they have smaller weights because they're interesting. So for example, a lot of the health studies oversample racial and ethnic minority groups because they're important and you wouldn't learn enough about them if you just sample people at random. Sometimes you oversample because the group is inexpensive. So people working for big companies get oversampled in business surveys because it's easy to make, IBM or Google or whatever fill in a survey. You know where they live. Whereas your local, your local papaya hot dog vendor, it's a lot harder to get all of them. And so you tend to take a small sample of small businesses and all the big businesses. And sometimes it just happens as a sort of uninteresting side effect that the weights are different. Then clusters, if you have to go and visit people, so sometimes you can just call people up on the phone or email them or whatever for a survey, but sometimes you actually have to go in person to visit them, to talk to them, or to take measurement, do medical exams in some of these health surveys. And if you're doing that, you want them to be close together. If you're hauling around a doctor's office with you in a big, set of 4 big tractor-trailer trucks, then you don't want to sample 5,000 people in random places around the country because that's a lot of driving. You want to park these things and get everybody you can locally. And so you have clustering. You sample cities or counties, neighborhoods, workplaces, schools, whatever. And you get less information per observation that way because all the people you get are, from New York or whatever, but in the New York cluster. But you get more information per dollar. And so it ends up being worthwhile. And then there are strata, which are comparatively unimportant, but they're one of the things that knowing what they are distinguishes survey people from other people. So if you sampled 1,000 people from the US, on average you get 10 from Iowa or 2 from DC, but they'd be random. So you might get unlucky and get no one from Iowa. So what you might do is to fix in advance and say we're going to sample exactly 2 people from Iowa, 10 people from Iowa, 2 from DC, and so on. And those are then called strata. And stratified sampling makes your sample more representative of the population. And so you get more information per observation. So those are the 3 things about surveys that you need to know. Now, that was sort of one stage of sampling. Once you've sampled clusters, if you sampled New York, you don't want to measure everyone in New York. You want a subsample. And so you might sample a bunch of neighborhoods in New York and go there. And then you might sample a bunch of streets in those neighborhoods and then go and knock on doors there. So you have multiple stages of sampling. Fortunately, you can ignore this nearly all the time. And if you look at data people have put up on the web, public use data, the data sets usually pretend that there was just one stage of sampling. This is an approximation that firstly makes it easier computationally, secondly makes it easier in terms of the size of the files, and thirdly helps with confidentiality. So everybody uses this approximation. They call it with replacement sampling, which is a terrible name, and it's that way for boring historical maths reasons. So when people say with replacement, what they mean is this approximation. And if you're running your own survey, you might know about the full, 4-stage sampling or whatever, but if you're using someone else's data, you won't. So the survey package in one slide. So there are two steps. You put your data into a survey design object. So you tell R what the sampling structure of your data is. And then that object then contains all your data and also contains the metadata about the survey structure. And you use that object where you would otherwise use a data frame. Now, unfortunately, you can't just, it wasn't possible to just, for example, take a function like LM and have a method for when the data is a survey design object, because LM already has inheritance and it's on the wrong argument. It's on the formula argument. And so, because of the way all these functions were set up, the ones that have methods and generics and so on, it's necessary to have new function names. It's not possible but the new function names basically have a SVY prefix. So survey mean does means, survey GLM fits generalized linear models, and so on. And they take the way most functions would take a data equals argument that's a data frame, they take a design equals argument that's one of these design objects. And that makes sure everything's kept together so it doesn't get lost. So now you know everything about the survey package. One of the things that's relatively unusual about it compared to other survey software is there's a lot more support for data exploration. So in the old days, sort of official statistics people, they knew what tables they wanted to produce, so they went and produced those tables. But now if you're using these data for modeling, for data analysis, then you want to do the same sorts of data exploration that you do with any data set. And so we want to make that possible. And sometimes that's easy, putting the weights into graphics. So a box plot, for example, you just need quartiles. And so instead of sample quartiles, you can use estimated population quartiles, the weighted estimates. A histogram, the box height depends on the number of observations in the box, once you work out the width and so on. And instead of the sample number, you can use the estimated population number. A kernel density estimate is just a sum of little bumps, little kernels, and you can do a weighted sum of little bumps. So those are all fairly straightforward. What's a bit tricky is scatterplots. So how do you weight a scatterplot? And there's a few ways of doing this. One, if for really big data sets, is thinning. You subsample the data set down so that points with a high weight are sampled with low probability, and points with a low weight are sampled with high probability. And that you end up with a smaller data set that's sampled with equal weight. That sounds inefficient, and in some ways it is, but if you're working with the American Community Survey and you have 2 million observations per year, you can't see that on a scatterplot anyway. You can afford to thin it down to a few thousand. Another way is to use the alpha channel of the picture, to use partial transparency, so that a point with low weight is almost transparent and a point with high weight is almost solid. And another way is hexagonal binning, where you conceptually stick a hexagonal grid over your scatterplot and squidge all the points down to the center of their hexagon. Usually you do this with a count of points, squidge them down. You can do a weighted count with the hexagonal bins, and I'll show some examples of these. So there's a survey plot function with a type argument that says how you want to do these, and there's a range of options. The first one, bubble plots are traditional. So there you make the size of the plotting symbol proportional to the weight. And you could do worse, but it's actually not very good, particularly for large data sets, because they all end up on top of each other. It's just a mess. Back in the Stone Age, it was the best you could do. Okay, so I'm going to do a sort of worked example. It's a health data set, very suitable given the food we've been having. So it's looking at dietary sodium intake and blood pressure in the NHANES study. So NHANES does health measurements, it does full medical exams, they take blood samples, they do lab stuff to them. They interview you about, what you eat and when you go to the doctor, how healthy you are, all sorts of stuff. So they measure everything the way they tend to with these big studies. They sample about 15,000 people every 2 years and report the data in 2-year waves. This is the example I talked about where the Mobile Examination Centre is towed around on 4 big trucks. And so they have, I think they've got 4 of them or maybe 6 of them, but they visit a fairly small number of places. So they've got highly stratified sampling, they've got a very small number of clusters. The data's all up there on the web. The design is actually a complicated 4-phase design, but the public use data pretends it's just one stage, and so that's what we're going to do. So we need to set up the data. This is relatively boring. It's just the main point here. The data comes in a whole lot of SAS transport files, and you just read them in. And you could do this with pipes and tidyversey stuff easily too. I'm just old. There is a tidyverse wrapper for the survey package called SRVYR, SRVYR, and people who like that sort of thing will find it's exactly the sort of thing they like. So weights, we're using, the data set comes with a whole bunch of sets of weights, depending on what sort of data you're using. Here we're using the dietary interview data, so we need to use the weights for that subset of the people. The weights, yeah. Yep. No, they give you, there's about 20 or 30 little data tables. And so this is what I'm doing here. So here I'm downloading, there's a demographic data table, there's a blood pressure data table, there's a body measurements one, which has got BMI, body mass index, there's a dietary recall one, and there's a whole bunch more. And so I'm downloading them and then I'm joining them. So this merge is the old-fashioned join, database join function in R. So I'm doing this here for the 2003-2004 wave, and here for the 2005-2006 wave, and here pasting those together into one big data table. And because that's 2 waves pasted together, it means the weights are wrong. So each wave has weights that add up to the US population, the US civilian non-institutionalized population. But if you've got 2 waves, they add up to twice that much. So I'm making a new weight that's just half of the original weights. There are also people in the file who aren't in the dietary interview. So there's everybody gets a clinical interview where the doctors talk to you and ask questions, or probably nice nurses talk to you and ask questions. But subsets of people get blood samples or dietary recalls, whatever. And so there are people in the file who aren't in our sample, and those people just don't exist from our point of view. Now, the documentation tells us the strata and cluster variables. They call the clusters PSUs because that's what survey people call them. It stands for Primary Sampling Unit. And you look up in the documentation, it tells you that the variable called SDMV PSU is the primary sampling unit, and the variable called SDMV STRA is the stratum identifier, and I've got no idea what SDMV stands for, but it's what the documentation says, and I trust them. So we say what are the unit identifiers for our sampling units. So that's this ID argument. So it says that the things we're sampling are these PSUs. The sampling of the PSUs is stratified by these strata, and individual observations are weighted by these weights. If we had multi-stage sampling, we would have multiple things here joined together with a plus. So we'd have the sampling units at stage 1 plus sampling units at stage 2 and so on. The data, we're only interested in the subset of the data table where we have, that's in the dietary sample that's got a non-missing weight. And this is a slightly annoying, so when I wrote the package, I decided it would be a good idea to have code to check that each cluster was in only one stratum, because that's an easy error you could make with your merging or whatever. Unfortunately, the National Centre for Health Statistics calls all its clusters either 1 or 2. And so there's a cluster 1 in every stratum and a cluster 2 in every stratum. And so you have to disable the checking, otherwise we'll tell you that cluster 1 appears to be split across all the strata. And then, so that returns an object. And that object has got the data in it, and it's also got the structure metadata. If you print the object, it tells you that it's a stratified one-level cluster sampling design with replacement, with 60 clusters, and you can ask for things like its column names and so on. And these are horrible names, but they're sufficiently consistent over time that you can Google them. This is the secret to how you could also read the code book, but it's actually easier to just Google them and let Google find the code book. Then a few minor data things. The dietary sodium and potassium are big numbers in milligrams per day. I'm going to turn them into small numbers in grams per day. And also, if I were doing this in another country, I'd have them in moles or millimoles or whatever instead of grams. SI units. So that's the update function. So this is like so this just adds variables to an existing object. Then we can ask for analyses. So what's the mean sodium and potassium intake? From this design object, and the usual NARM equals true. And the mean for sodium is about 3 1/3. Mean for potassium is about 2.5. Does anyone know what the sort of recommended maximum sodium intake is? What?
1.2.
Yes, well, you see. Yeah. And then here are quartiles. So there's, again, people are eating quite a lot of sodium on average. And so you can get means. You can get means from subsets. You may have, if you read a little bit of survey analysis sort of documentation or whatever, you'll see warnings that you can't just subset your data because that messes up the sampling structure. You can't just throw away the data that's not in the subset. Indeed you can't, but the subset function and the sort of square bracket subscripting all handle that properly. So the object does the right things when you subset it. What that means is it doesn't necessarily get a lot smaller when you subset it, because it has to keep a lot of the same information. Conceptually, what you do when you subset is you set the weights for all the observations outside the subset to 0. And then survey by, you can look at, here we're looking at, you specify a function, set of variables you want to analyze, set of variables you want it split up by, and what you want done to each one. And here I'm asking for the mean of sodium by race, ethnicity groups. And they're all quoted, all the variables are quoted with the twiddle, the model formula system. I could have used the tidyverse system, except that would have required time travel because this is older than the tidyverse. This is how we used to do non-standard evaluation back in the old days. Well, the tidyverse way is to have bare variable names and then do some deep magic underneath to quote them and then unquote them. It's nice for straightforward database operations. It makes it easier for new users, but it sure makes it hard for new programmers. They are simplifying. I mean, they're doing a lot to try and make it easier for programmers, but and this is one of the sort of questions of debate: is it actually worth it? Is the benefit to new users actually worth the cost to new programmers? And traditionally, the idea was for S and R was that it lured you down the slippery slope into programming. So if you do data analysis, you end up sliding bit by bit into coding, and that's harder now with all this extra. So you have to understand quasi-quotation, which is an area of programming that only a minority of people have ever had to understand in other languages. So here's a scatter plot. This is a weighted scatter plot using hex bins of diastolic blood pressure by age. I hope some people are looking surprised. So the thing about diastolic blood pressure it goes up and then goes down again with age. Basically, your systolic goes up and keeps going up, and diastolic goes up and down again. Your arteries stop being sort of rubbery and bouncy and just turn into pipes. And so the pressure is high when the heart is pushing and low when it's not. So you can see here the nice curve of the data. You can see the outliers. You can see that person up there who, with a very high diastolic. You can see these people down here who look a bit suspicious. So it's a good scatter plot for a lot of purposes. These people here, it's not precisely an error. It's not an error in the data. It's if you've remember having your blood pressure measured, they pump up a cuff and then they listen as they let the air out. There's a change in the sound that marks when your diastolic blood pressure, and the zeros are when they couldn't hear the change in the sound. And for these people, it's probably that the cuff wasn't quite the right size. And for these people, it's a mixture of the cuff not being the right size and them having very stiff arteries. So this is a real phenomenon of the measurement technology, though obviously these people do not have zero diastolic blood pressure. And then this is another version of it with transparency. And you can see some things more easily and some things less easily. So the outliers aren't as visible. You can still see these zero people, but you can see the top coding of age more obviously. So top coding is another thing survey people, official statistics people do. Everybody 85 means 85 or older, which is why there's this extra. So the scatter plots are useful and the different approaches show you different things. Okay, so some smoothers. Here, so survey smooth, we've got blood pressure against age for men and for women. The shapes are similar, but men's blood pressure peaks younger and higher slightly. Or quantile smoothers. So here we've got survey smooth, and there's a method argument that says you want quantile regression instead. And we get regression quantiles, which I think is a good way of looking at the distribution of the conditional distribution of a variable. Okay, and then a regression example. I'm going to do logistic regression with the outcome variable isolated systolic hypertension, which means that your systolic blood pressure is high, but your diastolic isn't. It's something that happens to older people. Almost everybody ends up with isolated systolic hypertension, whereas middle-aged people tend to end up with both systolic and diastolic being high. Okay, so we're defining a variable that says that your systolic blood pressure is high and your diastolic isn't. I'm defining some linear splines in age because we obviously don't want a straight line relationship with age. That's the point of the scatterplots. If you haven't seen, this is, so I like linear splines when talking to medical people because they're easy to interpret. The coefficients are slopes in different parts of the range. You don't get quite as good fit as you do with cubic splines, but the only thing you can do with cubic splines is draw a picture of them, and a lot of medical people don't like you doing that with regressions. And we've got a set of models being built up from the very simplest, just age, to ones that have got age, gender interaction, race, ethnicity, and sodium intake. And that all looks just like you do with GLM, except that you've got a design argument instead of the data argument. The family quasi-binomial, that suppresses a harmless but annoying warning. R will warn you with binomial if your weights aren't integers. And it doesn't matter. It doesn't affect the results at all if you put quasi-binomial instead of quasi-binomial. It's just you get this annoying warning. So here's a analysis of variance building up the model without just the sort of adjustment model with age, gender, race, ethnicity, interaction, likelihood ratio tests and so on. These are new. These are the Rao-Scott likelihood ratio tests there. Basically, the idea is that the likelihood ratio doesn't have a chi-squared distribution, but it's still a statistic. It has a distribution, and you can work out what its distribution is and do tests. That's fine. That's the statistic. That's its design effect, which says, you know, this looks big, but it's not as big as it looks because it's a noisy thing. We've got a comparison of the models with and without sodium with a deeply unimpressive p-value. There's very little evidence that sodium matters, which is a bit disturbing. So we can try some more variables, perhaps, you know, so adjusting for body mass index as well. Stick potassium intake in there because they're sort of related, sort of-ish. And again, deeply unimpressive p-value. Okay, so maybe it's nonlinearity. So we can stick in some splines in sodium intake, and we can do a test again for these, for that pair of terms. And, come back. And again, but not much, doesn't seem to be much going on. Now, there's a number, the reason this looks like this is because self-reported dietary data is so crap. So people who do this, if you want to do this sort of thing seriously, you get replicate measurements, you do measurement error modeling, and you could do all that with the survey package too. It's just that I'd have to explain regression calibration and stuff, and it would take another half hour. But that's the reason that we're not seeing a relationship is, I mean, there's a fairly, I mean, leaving out the side questions of causality, there's a fairly robust correlation between sodium intake and hypertension. But we can look at a continuous outcome. So here's systolic blood pressure as a continuous variable, and we're doing just a linear model. So we just leave out the family option. The default is Gaussian, is a linear model. And now we see that there is modest but reasonable evidence that sodium and potassium matter. We could look at the coefficients. Again, this is just like a generalized linear model, any generalized linear model, and we're seeing that sodium coefficient is positive and the potassium one is negative, as that's all as it should be. That's very nice. And we might feel a bit relieved, except that these are really small numbers. So this is the difference in millimeters of mercury per 1 gram difference in sodium intake. A gram difference in sodium intake is a lot, and a milliliter of mercury blood pressure difference is very small. So what we're seeing here is statistically robust, but meaningless from a health point of view associations. And again, this is largely the measurement error problem. If we'd ignored the survey design though, so suppose we'd just done a linear model for that, for blood pressure, without weights or anything, then the ratio, so this is the ratio of the wrong to the right regression coefficients, and it's quite wide. And this is the ratio of the wrong to the right standard errors, and you see they're underestimated by an amount that you'd care about, you know, half to a quarter. So it does make a difference taking the survey design into account. Other things we can do, ordinal logistic regression, so the proportional odds model, survival analysis, log linear models for contingency tables, rank tests. If you must do rank tests, at least you can do design-based ones that are proper, that do the thing they're trying to do properly. AIC and BIC, we invented how to do AIC and BIC for weighted model comparisons. And then sometimes you get designs specified by sets of basically bootstrap or jackknife weights. So they don't tell you the survey design information, they just give you a set of jackknife weights that sort of encapsulate it, and you can do that. And then there's functions to rescale your weights to match known population information. Then we did start a bit late, and we're running, yeah, it's okay. So, and then very briefly, two-phase sampling. So this is a more sophisticated problem. So here you've got a data set that you've got, a database or a cohort study or something, and then you want to go and measure some more variables on a subset of the people because it's too expensive to measure them on all the people. It's called two-phase sampling. The word phase versus stage means that the sampling is allowed to depend on the values of the data that you've already measured. This doesn't affect any of the computations, but it does affect what the Greek letters mean in those computations. So mathematical survey statisticians think it's very important that you distinguish between phase and stage, possibly even more so because it doesn't affect any of the computations. There are examples. A trivial example is case control sampling, where you sample everybody who has the binary outcome positive and a small subset of the people who don't have it. There's a technique where you take a random subset of people and then add all the disease cases later, or cases of whatever it is, fraud cases or whatever it is you're analysing. Or, you know, if you've got an outcome variable, an exposure variable, or sort of surrogates for them, approximations to them, you can sample based on both, and you get a more complicated sampling design with possibly more efficiency gain. So this sort of two-phase sampling, there's lots of opportunities to think about optimal design, especially if you don't have a non-response problem. So often when we're doing this, we're taking, for example, taking free text responses people have given us and then hand coding them, or taking blood samples people have given us and sending them off to the lab. And so non-response isn't really a problem. And so it's actually worth thinking carefully about design. Anyway, so here's an example. We've got, what do we need? We need to say, this is a data set from a children's cancer study. And we have to say, you know, this two-phase function looks basically like the survey design function, except there's two of everything. So there's a So the ID, we need to say what the sampling units are at phase 1 and phase 2. We need to say what the strata are at phase 1 and phase 2. We'd also need to say what the weights are at phase 1 and phase 2, except here, the weights at phase 1 are just equal, which is the default, and we don't need to tell R the weights at phase 2 because it can work it out for itself. And there's a sort of general principle that you don't let users enter data that the computer can work out because the users will get it wrong. And again, it just looks the same. The analysis of these two-phase samples just looks the same as you just have a different sort of design object and you plug it into the slot that takes design objects. But you can see if you print them out that they're more complicated. The other thing this shows is post-stratification. So if you take a survey, you take a sample, and then there may be some known population totals that you want to match. So if you're doing a survey of people, then you might want to match the census totals for, say, age, sex, and race. Or if you're doing a sample from a cohort that you control, there's all sorts of data you have that you might want to match the estimates of. And you get more information. By forcing your sample to match, you make it more representative. And so this is the fourth thing. This is the fourth thing about surveys, which is not a thing you need to know, but it's a thing that it's sometimes useful to know, is that you can force a sample to be more representative by reweighting it slightly. And this is what the calibrate function is for. And you tell it what variables you want to calibrate to. Generally, you also need to tell it what those true totals are. In this case, you don't, because in the two-phase sampling, it knows them already. It's got that in its data set. Yes, that's right. So it optimizes the weights. And it's very widely used for reducing non-response bias. So this is how opinion polls, electoral opinion polls, for example, aren't completely useless despite response rates of a couple of %. But you can, And it's got different names. I think it's, there's something called rim weighting, I think, in marketing. And so there's different names for it in different fields. Calibrate is actually a terrible name because, again, of namespace collision problems. There are too many things called calibration in statistics. Okay, so adding features. There are a lot of features in the package, but people keep wanting more, which is good. The best way to get features that you want added to the package is to ask for them, because I don't know what you want. I will add features that I think are interesting, but that might not be what you want. And ideally, ask with a published paper describing the estimator exactly, so I know what you're asking for, and a test data set so I can tell whether I've got it right. But, sometimes I do get requests from people saying, you should implement this thing, and when I look at I do a sort of Google search, whatever, and it turns out that nobody's worked out how to do it yet, and that's why I haven't implemented it. And in that situations, I may just work out how to do it, and that's how we got AIC and BIC and the rank tests. Somebody emailed saying, why don't you have, why doesn't the survey package do Wilcoxon tests? And because nobody's invented them yet, but okay, I'll think about it. One thing that won't be so effective for, mixed models turn out to be really hard, partly for non-obvious reasons. I mean, there's one reasonably intuitive issue, which is that mixed models are balancing a bias-variance trade-off in estimating random effects. And the bias-variance trade-off is different in the sample and in the population. But there are also other things like where do you even stick the weights in the estimator. So mixed models are hard and I'm working on them, but other things are more likely to be able to be just implemented. So where do you find all this stuff? The CRAN The survey package is on CRAN. The development repository for it is on RForge. I'm on Twitter. I have a blog, which also has random bits of technical stuff about the survey package on it from time to time. The survey LME, the mixed model code that's in development is on GitHub. These slides are on GitHub. Okay, thank you.
All right, we have time for some questions. We don't have a microphone, so I'm going to ask you to shout and you to repeat the question.
Okay.
Hand first right here.
I was just curious about the rank test part. I like rank tests because they're not parametric. Why did you say there's like a warning?
Oh, well, because the main, the sort of motivations for rank tests are firstly that they're exact, even in small samples, which isn't true of the design-based versions. And secondly, that they are sort of outlier resistant, and that's going to depend on the weights, on what the weights are like in things. So they're, and also the survey data is typically large enough that, t-test is non-parametric as well. So there are also things that they're sort of weird. The other thing about rank tests is they're not transitive, which is a weird technical property. But if you've got three groups, A, B, and C, then the Wilcoxon test can tell you that A is higher than B, B is higher than C, and C is higher than A. And that's all the rank tests except for tests for a single quantile do that. And I think it's a sort of unfortunate property. So it's a mixture of those things.
Thanks for the talk. So I noticed you mentioned, you had your list of things you can do in the survey package. Is it possible to take the design objects and use them in, say, another GLMNR, like if I wanted to do like a zero-weighted model?
So if you want to, you need to do some work. There are two relatively straightforward ways to do it, and I've got blog posts describing it. One is if you have replicate weights, these jackknife type weights, there's a with replicates function that runs any code you supply using the sets of replicate weights. So if you know how to do any sort of weighted, zero-inflated estimator, then you can do a properly survey weighted one. The other thing is there's a function survey MLE, which you give it a log likelihood or other objective function, and it will go and optimize it for you. So, and it knows it knows how to put in linear predictors. So if you wanted to do linear regression, which obviously you don't, you'd give it the standard normal likelihood and tell it to stick a linear predictor on the mu argument. And so if we look at I had a good example of this, but unfortunately it belongs to John Wiley and Sons, which was implementing negative binomial regression. And I'm going to put in some other count models, either myself or when I can get a student to do them. But here we've got a censored log normal example where you specify that's a censored normal likelihood. That's its derivative. And then you just say, use that log likelihood for each observation and stick a linear predictor with stick those predictors, a linear predictor on the mean variable, and just a constant on the standard deviation variable. So that, again, that will let you implement things. And you can probably get something that's a bit more computationally efficient with more work, but those two approaches will work for a lot of things.
On slide 38, you talked about the difference between using a complex survey design and just using an estimate, assuming there's no survey
Yep.
design. How often do you think people knowing this? And do I need to go back and shake the trees? And
To some extent, well, so when we wrote the rank tests paper, we went and searched on Wilcoxon and NHanes as keywords, and there are a lot of people who are doing the ordinary Wilcoxon test on NHanes. Basically, nowadays, if they're doing something that their software has a convenient survey analysis for, they're likely to do it that way. The main, I think the main exception to this is the general social survey, where I think people do tend to analyze that without taking the design into account. NHanes, I think they're more likely to do it right when that's easy, but they may well not notice when it's hard.
Is there a limit to the number of variables one can recalibrate?
It depends on the, there isn't a sort of specific limit, but you end up, the theory says that it should be small compared to the square root of the number of observations. And that's about all the theory says. Experience, sort of simulation experience, says that it will obviously start looking bad before the estimates break down. So you'll get more efficiency, and then you'll start getting less efficiency, and that will happen before everything breaks down and stops being valid. So it's fairly safe to add variables until if it looks like it's helping, it probably is helping. But there isn't any satisfactory theory.
Over there. So with job hiring, still on the other side of the room. All right, last chance. Oh, there you go.
The American Community Survey, they published the replicate weights.
Yes.
Can you just talk a little bit more about what, like a mental model of how
Yep.
this works?
Okay, so the simplest mental model for them is a jackknife. So
Can you repeat the question?
okay, so how the ACS, the American Community Survey, publishes these replicate weights, and how basically do they work? So if you think of a jackknife or a bootstrap, so a bootstrap, people familiar with bootstrap variants, when you take a bootstrap sample, you get some observations once, some observations 0 times, some observations twice. And so you could write that as a set of weights, where an observation that isn't included gets a weight of 0, an observation that's included once gets a weight of 1, an observation that's included twice gets a weight of 2, and so on. And so you can write, if you had like 100 bootstrap samples, you could write that as 100 columns of bootstrap weights. And if you multiply them by the original weights, you'll get survey bootstrap weights. Now, because of cluster sampling, the things you're bootstrapping aren't individual observations, they're clusters. And because of stratification, there's some tricky things about how you do the resampling within structures, within strata. But that's the basic idea. Now, the ACS uses, it uses a type, it's based on a design that has 2 clusters per stratum. And there, bootstrapping basically says you're going to split the data in half. You'll get 2 independent data sets that have 1 cluster per stratum. And that's the sort of, and then that's something called BRR weighting, as it turns out. That's a little, and then you have to look at all the possible ways you can split, you're splitting each stratum independently, and there's lots of possible ways you could do that. And you want to pick a carefully engineered set of them that picks up all the possibilities, that is balanced in all the right ways. And there are things called Hadamard matrices appear in this. And so it's relatively complicated in detail. But the basic idea is that it's a bootstrap. And that's what the ACS weights are. They give you 80 sets of weights, and they are conceptually a well-designed bootstrap sample at the cluster level, each one. And then, so you evaluate your estimator for each one of those 80 things, and then you take the variance of those 80 estimates, and then there's a scale factor of 1/4 for complicated reasons, and that's your variance estimator. The scale factor of 1/4 is because each of these things is only half as big as the original data, and that's how the math all comes out. But so it's basically 80 bootstrap samples that they've given you. And giving everyone the same 80 bootstrap samples, firstly it means that they can make sure they're nicely balanced, so you don't end up with any unlucky bootstrap samples. And secondly, it means that everybody will get exactly the same answer. Whereas if you were doing bootstrapping with only 80 replicates, everybody would get slightly different answers. And official statistics people don't like that, because it leads to, people saying, you don't get the right answer, my answer is this, your answer is that, and that causes paperwork and hassle, and so for what, as they say, face validity reasons, they try to avoid that, and so they publish their replicate weights. They don't encourage you to generate them yourselves. Is that? Yeah.
So you talked through an example where the survey data was collected in a very academic way. I'm not in an academic setting, and I've found that a lot of the survey data that I have to analyze or that I've sometimes collected is like the sampling methodology is unclear, the weights that need to be used on well-defined. What is the right strategy for working with survey data in that?
Yeah, so the question is about what do you do if you get the data and you don't really know what the sampling strategy and the weights and so on were. I think what I would do is to see if it was possible to calibrate it to some external data, then that would be a good way of getting more reliable weights. You do need to know what the sampling units were. So what did you sample individuals, or did you sample, school classrooms or whatever? But you should know that. If you don't know that, you're in trouble. And so for example, there's a nice exercise in Sharon Law's survey textbook that's a survey that was done by the American Statistical Association of its membership to ask how people felt about having a chartered statistician qualification. And it didn't come with any weights, but they know demographic information about the people who responded and about the association as a whole. And so you can then use that information to work out weights that would scale the sample to be representative of the association as a whole. So that's an example of something that it should have been done better, given that it was the American Statistical Association, but that it could be rescued by calibration to a known set of totals. And I think that's the sort of thing that could be quite useful for sort of wide variety. So traditionally, people got upset when you talked about doing this to things that weren't really probability samples. But so, for example, YouGov, the survey organization, their methodology is to collect rich calibration information and get a big sample, and not to worry about any of this probability sampling stuff, and to just say, you're going to model the sampling process statistically, and it seems to work. And basically all telephone sampling really relies on that sort of calibration stuff, because nobody gets useful response rates nowadays. So if your random digit dialing, which used to be the sort of gold standard way of getting samples, if your random digit dialing works, it works because your non-response corrections are good. Because even things like NHANES and the equivalent health telephone surveys, where they put a lot of money into sampling and people are relatively willing to help. The BRFSS, the telephone health survey, it's got a response rate just over 1/2. And they, that's when they do sort of 20 or 30 callbacks if they can't, to try and get to people. And, and people actually like participating in that sort of, well, more than they do in, electoral opinion polls. And so that sort of thing works, it clearly works in well-designed samples with non-response. And so it probably works in poorly designed samples with non-response. And there's some empirical evidence, both from YouGov and from some studies of different calibration approaches to this telephone health survey. There's some evidence that it really does work. But traditional survey statisticians hate people saying things like that because the idea of probability sampling is fundamental. And it is, it's just you can't do it anymore by telephone. So most of what I do, the sampling is this sort of two-phase sampling where you don't have non-response problems. You can do beautifully designed weighting, and weighting really works there. It's wonderful. But when you've just got response rates of 5% and dealing with the public and so on, then you're going to be relying on modeling the response process. And you just want as much information as you can get about it. And that's where sort of predictive machine learning approaches and so on might actually be useful too. Incidentally, there's a conference called Big Serve, an annual conference that is basically does that sort of thing. So what useful things can you do with predictive modeling and big data to help with survey problems?
Where is this conference?
Pass.
So Jared wins the hardest question from.
Yes, it appears to.
I got my own t-shirt. Oh yeah, we need to give out the t-shirt. Any last question while I get the t-shirt? Oh yeah, this whole side of over here.
Oh.
This is a strata or a cluster?
Well, it depends on how you that's a sampling question. It's not a question about the population.
Is there a multinomial logistic regression available?
Is there a multinomial logistic regression available? No. But it would be relatively straightforward to add, I think, because there are various packages that have got a non-survey one, and it should be fairly easy to add.
I was going to ask a personal question. What's the most exciting thing that you've done with this package?
Oh, it's the most exciting thing I've done with the package. Exciting. I mean, it's not really, exciting isn't really the right word. I mean, there's certainly, they've been, visiting, it's been visiting, people and survey organizations and, seeing that they're actually using it as, So when I found out that the Italian official statistics agency and the Portuguese official statistics agency were using it, that sort of thing is nice. And some of the research stuff is fun, but I wouldn't precisely say exciting.
I was searching for the right term. Huh?
Yes, but it is really. I mean, seeing people in serious official statistics organizations using it, and going and talking to them about it, and which bits of it they would like and which bits of it they change. Because I'm a relatively, when I started doing this, I was sort of new to the field. I wasn't a survey statistician, and historically they're a bit protective of their field. They don't want mathematical statisticians parachuting in and saying, aha, we can solve all of this with by considering polynomial hyperadmissible estimators or whatever. It takes a while to sort of get accepted by them as somebody who's probably okay.
decide. Since we are doing we are in conference using the NYR shirt, who you want to give this to?
Oh dear, that's it's not fair. Well, if it's supposed to be on most difficult question from a sort of technical point of view would be the what happens if you don't know what your survey design was.
All
So. Oh, sorry. Oh, missed. They're not as aerodynamic as the.
No, they're not. We need a t-shirt gun.
Need a t-shirt gun. They had one at our studio.
Yeah, they did. We need to get a t-shirt cannon, just so you know. All right, cool. That's going to happen now. All right, cool. So thank you very much. Big round of applause. That was awesome. Are you able to come to the bar?
Briefly, yes.